Hello everyone and welcome to this webinar. I'm pleased to present you one of the major new features in Vissim 8, the Mesoscopic Simulation. My name is Annette Ehlert and I'm part of the product management team. Also here is my colleague Johannes Schleich, who will follow in the chat and answer questions during the webinar. So in today's webinar, I will start with an overview about the different modeling levels and explain where the mesoscopic approach fits in. I will talk about the advantages of bringing in mesoscopic simulation into Vissim. I look at some use cases suitable for mesoscopic simulation, and then I talk about the algorithms and how they compare to microscopic simulation. This brings us to some of the requirements for network modeling, in particular for junctions. And eventually we'll see how you can combine the mesoscopic with microscopic simulation in a hybrid application and what results mesoscopic simulation has to offer. While going through this agenda, I will show you some examples and also demonstrate some of the functionalities directly in Vissim. So in transport modeling, we usually distinguish between different modeling levels depending on the detail that is taken into account. On one side, here shown on the top, there is a microscopic view where individual vehicles and the interactions with their neighbors are modeled. This is typically based on car following and lane changing models. In the Vision Traffic Suite, you would certainly associate these models with Vissim. On the other side, here at the bottom, there's the macroscopic level. Here aggregated values such as flow, density, and speed are taken into account. And calculations, for example for assignments, are based on the relationship of these quantities. These are typically projects and applications which are undertaken in PTV Vissim. The level in the middle is not clearly defined. There is still a wide range of possibilities of how to model traffic. Some of the approaches used are shown. For example, one can think of modeling individual vehicles, but they move through the network based on the calculation of aggregated values. Or vehicles move through the network as so-called packages of vehicles with similar characteristics. In another approach, there are simplified models of microscopic behavior, meaning vehicles are still moving based on car following models, but these models are much more simple. And also cell-based approaches have been used. In these models, the road network is divided into cells, and depending on how many vehicles fit in such a cell, the approaches are subdivided in microscopic and mesoscopic models. So we see that the mesoscopic level is less well defined, but it clearly differs from the microscopic and macroscopic definitions. We will see that when we come to the description of the algorithms. So the biggest advantage of mesoscopic simulation is the simulation speed. To demonstrate this, I'll show you one model which is simulated microscopically. This is on the left side and in the mesoscopic simulation. You will not see any vehicles in either of these simulations as they are both run in the so-called quick mode. So please have a look at the simulation time in the status bar. The mesoscopic simulation is finished, while in the left model we haven't reached yet 400 seconds. Just to highlight that another time, we see it once more, but the simulation time only. So we see again that the mesoscopic simulation is quite fast. So we currently estimate that the factor for the simulation speed compared to micro is about 30 to 60, depending on the model, in particular on the number of signals and on the number of vehicles in the network. So what are typical use cases for mesoscopic simulation? Generally, one can say mesoscopic simulation should be used if you model a reasonably large area where the measures that are evaluated have an impact on route choice. Or if you put it in other words, with the measures implemented, for example, in a do something scenario, you cannot assume that the drivers will stick to their original routes. This could be, for example, corridor models with a wider area than just the corridor, where you modify, for example, junction control. and the changes have potentially an effect on route choice. This could be measures to relieve congestion and again may result in drivers using different routes. Or this could be scenarios where you evaluate the effect of construction sites or generally temporary closures of road infrastructure. One can specify use cases in terms of supply and demand, meaning that you want to simulate models with varying demand over time and also changes on the supply side. Like I said before, speeds, for example, could be changed, signal timings during the simulation. And as a result of these changes, you would like to monitor, for example, the build-up and relief of congestion over time. So now you can argue that this could be done using microscopic simulation, but there are two arguments that would favor mesoscopic simulation. First of all, the size of the model. If we talk about route choice, we talk about dynamic models, and the iterative dynamic traffic algorithm is quite time-consuming. And second, the level of detail for the results. If you don't need results for individual vehicles, but are satisfied with aggregated quantities over short periods of time, say 3 to 5 minutes, then micro is not necessarily needed. So the choice is mainly determined by the requirements with regard to runtime and the detail of results. So the next question is, what is the best way to obtain a model for mesoscopic simulation? As mentioned, these models can be quite large, with an extent that allows to also evaluate the impact on route choice. So the easiest way to create a big network that is suitable for meso simulation is via the abstract network model. If, for example, you have a fully coded network in Vissim available, then use the A&M export from Vissim and the A&M import in Vissim to obtain a Vissim network for which you can use mesoscopic simulation straight away. I will demonstrate this now in Vissim. For this, I have a prepared network exported from Vissim, and I will use the A&M import to import this network. I will choose the network. For the dynamic traffic data, you need to choose the dynamic assignment option that is independent of the import of routing. In this case, we have a A&M route files which contains only matrices, so that means you don't need necessarily an assignment result in Vissim. So I will import this model. So and the only things you now have to do is you have to set the parameters for dynamic assignment. For example, you need to set the convergence criteria. For the iterative approach, you need to change the number of runtimes. And now the only thing required for mesoscopic simulation is the change of the simulation method. And if you want to speed up the simulation even more, you choose the quick mode and run the simulation. And in this case, we will see that the model converges within 3 iterations. So we have seen that there are only a few steps required to run a mesoscopic simulation in Vissim once you import a network from Vissim. So how does a mesoscopic simulation work within Vissim? This is now first an overview, and after that I will go into this in more detail. As we have already seen, your model must be for dynamic assignment. Car-following model is a much more simplified algorithm. The same applies to the lane changing or lane selection. This affects, in turn, how junction control is modeled. And the mesoscopic simulation uses a network graph consisting of nodes and edges similar to the dynamic traffic assignment graph. So I will start with a dynamic assignment. So if you use dynamic assignment in Vissim, there is no changes compared to the microscopic simulation. It works in a way we know it in steps. You start with a route search, and then the vehicles are distributed to vehicles, to paths, and then the simulation follows, meaning that the vehicles are traveling along their assigned paths. And then the evaluation of costs follows for the paths and the edges. And then there is a convergence check. And if the termination criteria are not met, then the iteration starts again. So the only changes is for the simulation, because the vehicles move based on the mesoscopic algorithm. So to show that in a different way, in fact, we see here a screenshot from the manual. If you now opt for the dynamic assignment, you basically have three options to load the demand onto the network: the microscopic simulation, the meso simulation, or a combination of these two, which is called hybrid. We will come to that later on. So the big advantage is that these options are exchangeable. Because the edge and route evaluation is based on the dynamic traffic assignment graph, you can easily switch between these three different modes. So of course the parameters must be set according to the simulation method, micro or meso, but it is not necessary to produce new path files, for example. So the mesoscopic simulation uses a different car following model, which is much more simple than, for example, the models by Wiedemann. It requires only three parameters: the desired speed, the standstill distance between two vehicles, and the reaction time. For car following, we distinguish between two different states, which are shown in the formula at the bottom of the slide. So the position of the vehicle is calculated as the minimum of these two possible states. So the first state means that vehicles move with their desired speeds, as long as they are not impeded by a slower vehicle in front. And the second state describes the situation when there is a vehicle in front. Then the temporal distance to the leader corresponds to the reaction time, plus the time it takes to travel the standstill distance. Note that acceleration and deceleration are not modeled. So to demonstrate the effects of these three parameters, I'll show you some simple animations with varying parameter settings. Vehicles move from the left to the right, and there's a traffic signal at about 150 meters where the vehicles may need to stop. So first, we vary the reaction time. As we expect, the distance while driving is bigger, and we also see that the queue moves faster with a slower reaction time. Second, we vary the standstill distance. Here, as the parameter indicates, the distance at standstill is bigger, which affects the maximum density on a link, and also how fast the queue moves in the upstream direction. And third, the desired speed differs in the two animations. Also here we see that this has an impact on how the queue moves in the upstream direction. So you can basically use these three parameters to calibrate your model. So in Vissim, two of the following parameters can be defined in the driving behavior, namely the reaction time and the standstill distance. And the desired speed is a characteristic of individual vehicles defined by the desired speed distributions. The speed of a vehicle can change on its path by crossing, for example, reduced speed areas or desired speed decisions. So next we look at lane changing and lane selection. Also here some simplistic rules apply. In the mesoscopic simulation, vehicles do not change lanes on a link. Nevertheless, vehicles must use certain lanes in order to stay on their routes. This is considered by the lane selection model. So the lane selection takes into account lane closures, for example. Vehicles can only travel on lanes that are open for the corresponding vehicle class. The lane selection takes into account the lanes that enables a vehicle to stay on its route. If downstream, a certain turn can only be reached from one lane, and the vehicle must make this turn, it enters the link on the corresponding lane. If several lanes can be used to reach the next link downstreams of the next node, then the lane is selected based on density. So one consequence of this lane selection model is that lanes which do not have a connector to another link downstreams are not used at all. So far, we have seen that the mesoscopic simulation makes use of a simplified car following model, and also lane selection works based on some simpler rules. The simulation works event-based. What does it mean? In microsimulation, the position of all vehicles are updated in every time step. In the mesoscopic simulation, the car following algorithm is solved differently, meaning that we calculate the time when the next so-called event for a vehicle occurs. Such an event could be when the downstream node is reached, or when the signal switches to green and the vehicle can enter the node. So once we know this time, an event is scheduled. So we do not need to look at this vehicle, for example, when traveling along the link. So these events are then processed in the order they occur over the time in the simulation. This reduces the calculation efforts quite considerably and consequently speeds up the simulation. But as a consequence of this, individual vehicles cannot be visualized during mesoscopic simulation, and also vehicles behave differently at junctions. Remember that acceleration and deceleration are neglected. Junction control requires different parameters, and there are also some special rules for the definition of nodes for certain intersections. So junction control between conflicting volumes is modeled using signals and gap acceptance. Signals can be modeled in the usual way. They must be fixed time, but can have daily plans. So different fixed time control over the course of the day, for example. Gap acceptance is slightly different. So it works with conflict areas, and it basically requires 4 steps. First of all, you need to define the conflict, and then you need to define the 2 parameters, the critical gap and the follow-up gap. And also the maximum waiting time must be defined. So once the conflict status is defined, the next step is to define the gap values. As we will see, the definitions follow common guidelines like the Highway Capacity Manual or the German version, the HBS. So we start with the critical gap. What is a critical gap? The definition as well as the values are similar to the Highway Capacity Manual. According to the HCM, the critical headway is defined as the minimum time interval in the major street traffic that allows intersection entry for one minor vehicle. In Vissim, it is similar. The critical gap corresponds to the time it takes for the follower to move the distance, here shown by the red arrow. So basically, the critical gap determines how the capacity of the minor stream decreases when the volume on the major traffic stream increases. So in Vissim, there are special lists for entering gap acceptance parameters, Y, Z, because these lists show only the conflicts relevant for mesoscopic simulation. The example here is a left turn from the major street that has to give away. It is a rank 2 movement that must cross the oncoming traffic stream. In order to enter the parameters, you can use, for example, coupled list. In this case, the coupled list of nodes and meso turn conflicts. You can select the node on the left side, and then you will see the corresponding turned conflicts in the node on the right side, and you can first highlight and then enter the value for the corresponding conflict. So the follow-up gap is quite similar. The HCM states the time between the departure of one vehicle from the minor street and the next vehicle of the minor stream is the follow-up gap. So consequently, the follow-up gap is the headway that defines the saturation flow for the minor road if there were no conflicting vehicles on the higher ranked movement. Also for the follow-up time gap, there are specialists, which is called meso turns. Again, you can use coupled list. On the right, you have the node list, and on the left is the meso turn list. And highlighting a node will show you the corresponding turns from mesoscopic simulation. So for example, in this case, the default value is 2.2 seconds. So the next question is how to calibrate these parameters. So when importing an A&M file, all the parameters are set using default values. These defaults are validated against the HCM, so you will also find the values in the Vissim manual if you set up your model in Vissim directly. You may also need to calibrate these parameters using some observed data. So then you would basically follow the procedure like I'm showing here now. The graph shows on the y-axis the potential capacity of the minor stream, and on the x-axis the conflicting flow of the major traffic stream. So how do the parameters affect the curve now? First, the follow-up time gap. It determines the intersection point with the y-axis. As we have said before, the saturation flow when there is no traffic on the major road. Second, the critical gap. The critical gap determines the shape of the curve. In this example, there are several curves for different critical gap values, and you can see that these have an impact on the shape of the curve. And then the maximum waiting time, we have not touched that yet. It determines the capacity of the minor stream when the major street traffic operates at its maximum. So basically it defines the number of vehicles that can squeeze in the major traffic stream. So you can also combine the mesoscopic simulation with microsimulation in a so-called hybrid model. So you define an area in which you simulate traffic microscopically, whereas in the rest of the model, the simulation is based on the mesoscopic algorithm. So why would you do this? This can be useful if in a model you would like to investigate a smaller area in much more detail. For example, you need vehicle records or certain measurements from the simulation, and that means the results must be more detailed than the mesoscopic simulation can produce. Other reasons for hybrid are that you have elements in your model for which the meso simulation is not applicable. For example, you have vehicle-actuated controllers, public transport priority, or in certain parts of the model, you have interactions with pedestrians. So of course, in such a simulation, some vehicles should choose routes through the area, as shown here. And other vehicles will not touch the area and choose routes around the area. So what is important for such a model is that the evaluation of routes across the micro area is consistent with the one in the rest of the model. So in other words, vehicles should not choose to avoid the micro area because routes around it are much more attractive. This is the case in Vissim because the evaluation is based on the dynamic traffic assignment graph, which is generated for the entire model. And also the generalized costs are then evaluated based on the results of the corresponding simulation method. So furthermore, it is important that the introduction of microscopically simulated areas does not result in any artificial behavior. In other words, certain phenomena must be replicated across borders. So, for example, shock waves must be replicated across the borders between the microscopic simulated area and the other part. And for a quick comparison, you see on this slide the same model 3 times, simulated in 3 different ways. On the top you find micro only. In the middle there's a hybrid model with the microscopic simulated area. And on the bottom there's a pure mesoscopic simulation. So the individual vehicles can only be seen in the microscopic simulated model and in the hybrid model. So the color represents density, and the darker the density is, the more the Q moves in the upstream direction. Over the course of the simulation, you will see, or you have seen, that the Q extends in all models to the beginning of the network. So now I will demonstrate a hybrid simulation in Vissim. I will continue with the model I have imported. First of all, I will change the settings for dynamic assignment, disable the convergence criteria, and I also change the simulation parameters to one simulation run. So in order to model a hybrid model, you need to define a section, or what is called in Vissim sections. So you basically have the option of a rectangular shape, or you can do it like I'm doing now here. I just click around an area, user-defined, and in this area the simulation will be microscopic. So the only thing you need to do now is to activate this area for the microscopic simulation. You can do that in the simulation parameters. Select this area, and then we run the simulation. So at the moment we are still in the quick mode. You will not see any vehicles, but if I switch that off, you can see in the microscopically simulated area the vehicles. So, and as we have also noted, you can use the same path file produced before for the dynamic assignment. So you can, of course, have several of these sections in your model. And of course, there's also an impact on the runtime. Microscopically simulated areas will slow down the runtime. So the next thing I will like to show you in Vissim is something about the evaluations. Of course, there are some new evaluations for mesoscopic simulation, but there are also some evaluations which you can use, for example, for a hybrid model where you would like to have results for the entire model. So in this case, I will switch on all the evaluations which can be used for a hybrid model and for mesoscopic simulation. You can use the link evaluation. There's a new evaluation for meso edges, and you get the results of the vehicle network performance, and also there are some new results for OD pairs. I will now produce here results for the vehicle network performance for the entire simulation time, the same for the OD pairs. For the links, I will use an interval of 300. You may need to know that the interval must not correspond to the evaluation time of the dynamic assignment. You can choose different intervals here, and for the meso edges, I will choose 600. And I will also enable the link evaluation for lanes. So in order to see some results during the simulation, I will change the graphic parameters. I will use a color scheme. And then I will see here the lane segments which I have selected in the evaluations. And I will now choose density and define the classes accordingly. Okay, I've also prepared a layout file which contain all the layouts for results. So and now I can run the simulation, and if I do not run the simulation in quick mode, the color of the links will change after 300 seconds when there is a new result for the evaluation. And again, we in the microscopic simulated area, we can see some vehicles moving. I can also switch that off and run the simulation again in quick mode. So on the bottom, we have now the lists which are produced for this hybrid simulation. We have the network performance list. That is a list you know already. There are some average values, for example, for speeds, and some totals for the network, for example, distance, travel time, and delay, and also vehicles which have arrived and which are still in the network. Then there are also some new lists, for example, for lanes, for meso lanes. This is a result list, which you might not, which you cannot synchronize with the network. So, but you have the results in this list, but you can, for example, use the meso edges list and a coupled list, for example, with this meso lanes. And one result which might be of interest is the queue length. So if you now select an edge and you synchronize this list, you can see here the corresponding queue length for this particular lane. So I will go back to the presentation. As we have seen, there are some new evaluations for mesoscopic simulation with a variety of different outputs. And we have also seen that some options are commonly produced for the entire model if, for example, you choose to model a hybrid model. There are also some evaluations which are particular for mesoscopic simulations. These are related to the mesoscopic network graph and are, for example, for the edges. And some of these results depend on the type of the edge. For example, for turns, you have the option to look also at link results of the incoming link for the vehicles that make that turn, for example. So on one side, there are many new possibilities with the mesoscopic simulation, but there are also some limitations which are partly due to the algorithms used. So these concern mainly slow modes such as bikes and pedestrians, but also some other elements. For example, you cannot use real parking spaces, or you cannot work with priority rules in a mesoscopic simulation. We have already also seen that vehicle-actuated signals can be modeled, but you need to define sections in which you simulate microscopically. So now we come to the end of this webinar. For more information about Vissim in general, please check our website and the materials provided with the installation or the demo version. For the mesoscopic simulation, you will find more in the overview document of Vissim 8, and there are also some additional examples in the installation. If you have any questions on that topic or would like to share your comments, you can contact us. We will still answer questions in this webinar session and other questions also afterwards by email. I hope this webinar was of interest to you, and with this I would like to finish the presentation. Thank you.